Hello and welcome again to my physics online video lecture series. Today's video I'm going to be talking about motion in two dimensions, with specifically the discussion focusing on trajectories. We have at this point discussed vectors, and we've discussed motion in one dimension, and we've discussed kinematics of motion in one dimension. So now we're planning to discuss the kinematics of motion in more than one dimension. So what is a trajectory for starters? Well, a trajectory just is kind of the path taken by an object that is essentially moving under control of one or more forces. Now, generally speaking, this set of given forces may be constant. For example, the simplest trajectory might be launching an object by projecting it, so it becomes a projectile, and only gravity is working on the object. So a projectile on the moon, for example. A slightly more complicated trajectory may have variable forces, but it's sort of the same force acting at all times on the object. The result of that, in terms of what we've covered so far, is you have a varying acceleration. But in general, that acceleration has a predictable direction and maybe tied in some way to other parameters of the object's motion. So for example, air resistance creates an acceleration in the opposite direction of the object's motion at all times, and the magnitude is dependent upon how quickly the object is moving relative to the air. Similarly, if you have a missile and it produces thrust, that thrust produces an acceleration that is in a known direction and tends to be have a magnitude that depends on how fast the exhaust from the rocket thrust is moving and how much, like, per unit time is leaving from the rocket, that kind of thing. So we're kind of assuming here that the acceleration on the object is knowable and has some consistency to it, whether it's constant or not. And for an algebra-based physics class, generally speaking, the acceleration has like a constant magnitude and maybe a constant direction, at least relative to the motion of the object. So we'll kind of assume constant acceleration, or constant, we could call it relative acceleration. And so what that would mean is, if I have an object that is moving in this direction and the acceleration happens to be like this, one version of constant acceleration might be that sometime later the object is now moving in this direction and the acceleration is still straight down like this. So that would be like one version. The other might be, for example, uniform circular motion. So at one moment in time, the object is moving like this and has an acceleration this way. And then at another moment in time, maybe the object is moving like this and the acceleration is now this way. So the acceleration is kind of perpendicular at all times to the velocity in this case, and with equal magnitude relative to that velocity. Okay, so those are different versions of a trajectory. Now, how do we actually handle it in physics? Well, generally speaking, the equation is still valid to say that the position, and I'm going to represent position here as an S with an arrow over it. So let's let this be position vector. Then that vector might, for example, be representable as an X, a Y, and a Z. Okay, velocity vector in this case would be like so, and so V might be represented by Vx, Vy, and Vz, again in 3 dimensions. And the acceleration vector would be like this. And we can add subscripts like I for initial. So here's your acceleration vector. It would have an AX, an AY, and an AZ. You might have like an initial velocity vector, VI, which could be represented by VXI, VY, VYI, and VZI. You could have an initial position vector, which could be represented by the initial X, the initial Y, the initial Z, etc. Okay. Well, as it turns out, in motion with more than one dimension, it's still valid to say something like position at some time is given by 1/2 of acceleration times time squared plus initial velocity times time plus initial position. And this is, of course, for constant acceleration. It's just that each of these terms now has more than one component to it. So this is constant acceleration. What does it mean that it has more than one component? Well, we'll get to that in just a moment. Just be satisfied with the fact that you have a vector times a scalar times a scalar, you have a vector times a scalar, and you have a vector. All 3 of these things are vectors. So this could be rewritten as 1/2 t squared, the scalar term, times the acceleration, the vector term. So we have scalar, we have vector. This could be t times v initial right here. So scalar times vector. Scalar times vector. Initial position just is a vector, but if you want to call it scalar times vector, it's 1 times, the scalar is 1. So you have scalar times vector. And so you're basically just adding 3 vectors together to get your resultant vector. So all that discussion that we had previously about how to add vectors together, whether in Cartesian, whether in polar, in 3D, whether in Cartesian or cylindrical or spherical coordinates, all that is still valid here. In fact, this is a good application of it. Now, with that said, for a lot of kinematics problems, it's kind of easiest to work in Cartesian. Now, why is that? Well, for example, maybe you have projectile motion. So we will talk about projectile motion in its own video. Probably actually going to be more than one video. But in projectile motion, free fall, object is in free fall, the acceleration vector could be represented as 0, 0, g, or negative g, where negative g is your free fall acceleration. And this is if you want it in 3D. In 2D, so this is 3D. In 2D, a might be represented by 0, negative g. This is 2D x, y. 3D x, y, z. We usually use z to represent vertical when you're in 3 dimensions. Although I suppose you don't specifically have to do it that way. In any case, what this means is that it's easier to work in Cartesian. So a 2D motion, let's just do 3D motion. 3D motion, 3D trajectory becomes, and basically remember that in 1 dimension each vector just means a plus or a minus sign when you're in Cartesian. So 3D trajectory would become x is equal to 1/2 ax t squared plus v initial x, or vx initial if we're being consistent with my previous notation, vx initial, times time, plus x initial. The y component is 1/2 ay t squared plus vy initial time plus y initial. And the z component is equal to 1/2 az t squared plus v z initial times time plus z initial. Now you'll notice that in all 3 equations, it's true to say that only the x components affect x, only the y components affect y, and only the z components affect z. Okay? So once you've gone to Cartesian coordinates like this, whether it's in 3D or whether it's in 2D, you can kind of like treat each of these coordinates independently from the others, but we do have one common linking or coupling parameter, namely the time is the same in all of these. So at time 1 second, t equals 1 second in all 3 equations. So that lets you get the position x, y, z at 1 second. Okay, so let's do a quick example. You have an object, it's moving in 2 dimensions, the xy plane. It's initially at the origin, so that gives us an initial position. It also has a speed of 2 meters per second in the positive x direction. So that gives us the initial velocity. Namely, the x initial is plus 2 meters per second and the y initial is 0. Finally, we're told that it has a constant acceleration of 0.75 meters per second in the negative y direction. This is basically telling us that the acceleration is 0, negative 0.75 meters per second squared. That is to say the x component of acceleration is 0 and the y component is negative 0.75. So we want to know where the thing is, where this object is, after 4 seconds. So this right here, this 4 seconds later, this is your time. The question, where is it, means we're looking for S. Okay. Well, basically S can be represented by x, y. Could also be represented by r comma theta. But in any case, x is given by 1/2 ax t squared plus v x initial times time plus x initial. So if we plug in these numbers from above, what we end up getting is 1/2 times 0 times 4.0 seconds squared plus v initial, so in x, so that would be plus 2.0 meters per second times 4 seconds plus 0 meters. Okay, so that gives us a final x position of 8.0 meters. Okay, we can do the same basic thing for y. It's going to be 1/2 of ay t squared plus v y initial time plus y initial. And so that ends up looking like 1/2 times negative 0.75 meters per second squared times 4.0 seconds squared plus 0 times 4 seconds plus 0 meters. Okay, so this ends up being negative 6. Y final would be negative 6 meters. So if I take this y final and this x final, I can put them together to get the final position, and it can be represented as 8 comma negative 6 meters. Since we haven't specified whether this needs to be in polar or Cartesian, this suffices for the answer. We could, however, convert it to polar. The result will be 10 meters away from the origin in a direction of about 323 degrees counterclockwise from the positive x-axis. So that is all for today's video. This was just meant to introduce the idea of trajectories and of using what we've learned in the past about adding vectors in order to solve for basic trajectories. We'll apply it in the future to specific kinds of motion like projectile motion. So again, that's all for today's video. Hope you learned something from it. Thanks for watching.